Welcome everybody to another session of Nairo. I'm Srijit here, and today I'm continuing the applications of AMS BAND. And in this specific session, I'm going to brief you about the density functional theory plus Hubbard U using AMS BAND. So speaking about Hubbard, before that I would like to brief you quickly about density functional theory, which is widely used quantum mechanical method for calculating the electronic structure of atoms, molecules, and condensed matter. So while DFT often provides a good descriptions of many ground state properties, it can struggle with strongly correlated systems, particularly those containing transition metal or rare earth elements with the localized D or F electrons. These systems often exhibit phenomena like not insulator behavior, where materials that should be metallic according to the band theory are actually insulated. So the concept of DFT plus Hubbard U, this method is an extension of DFT designed to address these shortcomings. So it introduces an on-site Coulomb interaction term, the Hubbard U, to the Hamiltonian. So this term penalizes multiple occupancies of the localized d or f orbitals on the same atom, effectively opening band gaps in Mott insulators and improving the description of magnetic properties in electronic structure. So in this typical example, I have taken here a nickel oxide, a metal oxide. So in this context of using how we can implement it through AMS BAND, which is a periodic DFT module within this suite. So the DFT-U method or DFT plus U method is implemented to handle such strongly correlated materials, as I discussed, like metal oxides. When performing calculations in AMS BAND, we can specify the Hubbard U parameter for specific atomic orbitals, which involves defining which element and which orbital, for example, D or F, should have the U correction applied along with the value of U, typically in atomic units or in electron volt. So what are the key aspects of a DFT plus Hubbard U in AMS BAND? So I have taken this example and you can see that what are the different calculations I have done as a setup. So I'll brief it step by step. So first one is addressing the strong correlations. So the primary goal is to improve the description of electronic structure, magnetic properties, and insulating behavior in systems where standard DFT using LDA or GGA functionals fails due to this functional GGA BP86 has been taken in this example, which fails due to strong electron-electron interactions. The another case is localized orbitals. So the Hubbard U correction is typically applied to the localized d and f orbitals of specific atoms in the system, as these are the orbitals most affected by strong on-site Coulomb interaction. So I can share you an example here. I have already run the calculation. So here, if I take the density of state, so it will show you a typical example. So I need to select one nickel atom and just see. So this is actually the thing which I have just mentioned about d orbitals, f orbitals, and the correlation diagram. So how this U parameter, the Hubbard U parameter, represents the effective on-site Coulomb repulsion energy. So if I take this example, you can see that variation in electron volt against density of state. Okay, so that's what I have introduced in the introduction. So I will brief a little bit, elaborate in the next videos, but let me finish this intro. So this Hubbard U parameter represents the effective on-site Coulomb repulsion energy, which values can be determined empirically by fitting to experimental data or calculated using ab initio methods like constrained DFT or linear response. Implementation in AMS BAND, which provides a user-friendly interface to set up the DFT plus U calculations. So we can specify the U value and the orbitals it applies to within the input settings of the calculation and how it will impact on the electronic structure. So the inclusions of this Hubbard U term can lead to significant changes in the calculated electronic band structure, such as opening of the band gaps, the shifting of energy levels, and changes in the bandwidths. So the projected density of state or PDOS is a powerful analysis tool which is used in this material science calculations to understand the contributions of specific atomic orbitals to overall density of state. So this density of state itself describes the number of electronic states at each energy level in the system. So the PDOS goes a step further by projecting the density onto the specific atomic orbitals. For example, 2s for oxygen, 3d for iron, providing insights into the orbital character of the electronic bands. So in the next video, I will show you that how we can differentiate with Hubbard and without Hubbard, what will be necessary impacts in electronic structure calculations. Thank you.